In the chemactivity 11 and the corresponding videos, we will revisit mass-to-mass stoichiometry in balanced chemical equations, but now from the context of trying to find out which reagent is limiting and how much of the other is in excess. To start off, let's use a little bit of an analogy. We're going to look at making sandwiches. So I have a recipe for a sandwich: 2 slices of bread, 4 slices of ham, 3 slices of cheese, 6 pickles. I'm not saying it's a great sandwich, but it is in recipe. And we can write out this recipe kind of like a balanced chemical equation. So 2 slices of bread, 4 slices of ham, etc. And all of this leads to making one sandwich. So before we go on, I have a question for you, and I'd like you to think deeply about this question. And the question is, given this recipe, how many sandwiches can we make? Now, I'm sure a variety of answers came in, and in some ways it's a bit of a trick question. But actually, the best answer here is we have no idea how many sandwiches we can make. What we need to do, first of all, is go to our pantry and our refrigerator and figure out, well, how much bread do we have? How much ham? How much cheese? How many pickles? Do we need to go to the grocery store and get some of these things? So at this stage, we have no idea how many sandwiches we can make. And this is quite relevant in terms of thinking about chemical reactions. You can have a balanced chemical equation, but you don't know how much product will be formed until you know how much of each of the reactants that you have. So it translates quite nicely to thinking about chemical reactions. So then let's change this a little bit. We actually do know how much of each of these things we have. We checked out our pantry and our refrigerator. And as it turns out, we have 48 slices of bread, 60 slices of ham, 60 slices of cheese, and 72 pickles. Note that we actually have the most pickles present. And that'll be relevant in a minute. So with this first question here, I've got a little bit of a chart, and I'd like you to think about, well, what would be the maximum potential number of sandwiches that could be made when each ingredient is examined individually? To give you a sense of what I mean. So given 48 slices of bread and that each sandwich would require 2 slices of bread, I think we could predict, well, we could possibly make 24 sandwiches. So I'd like you to go through that same calculation for the other ingredients. So of course, if we think about the ham, we got 60 slices of ham, but we need 4 slices for each sandwich. We'll take that 60 and divide by 4, so we'll get 15 potential sandwiches. For the cheese, we could potentially make 20 sandwiches. And for the pickles, well, we could only make 12 sandwiches. So even though the pickles are present in the largest quantity, actually, they are what determines the amount of sandwiches that can be formed. And you're going to see we're going to call them the limiting ingredient or the limiting reagent. They're actually limiting even though they're present in the largest amount. So as it turns out then, 12 is the maximum number of sandwiches because we'll run out of pickles before we run out of the cheese or run out of the ham or the bread. So the bread, ham, and cheese are all in excess. And we'd say that the pickles are the limiting ingredient. Note the process that we just went through. And that is, we predicted how much product or how many sandwiches would be made for each of the different ingredients. And whichever one resulted in the smallest amount of sandwiches, well, that's the limiting reagent then. The other thing that we can do with all of this information is we can prepare what's called an ice table. Now, I'm sure many of you are familiar with this idea of ice table, although usually that's in the context of equilibrium type reactions. In this case, this is a non-equilibrium ice table where instead of concentrations, it's actual numbers of reactants and products. So we'll still abbreviate it as ICE, initial change, but instead of at equilibrium, it will be at the end of the reaction. In completing an ice table, you list initially all the initial amounts of the reactants. Of course, it'll be 0 sandwiches because the reaction hasn't happened yet. And then, because we know the pickles are limiting, we'll know that all of those will get used up. And notice it's negative 72 because they're consumed. And we know that 12 sandwiches will form. Now, in order to complete the rest of this ice table, we need to consider the proportions. So note, for the initial part, that has nothing to do with the balanced equation. and only everything to do with what was in the refrigerator and what was in the pantry. But at the level of change, we need to think about the balanced equation. Note that in terms of pickles compared to sandwiches, it's 6 pickles for 1 sandwich. So pickles are 6 times larger than the number of sandwiches. In a similar way, it's 72 pickles compared to 12 sandwiches. 72 is 6 times larger than 12. So in the same way, if we want to figure out, well, how much bread will get consumed, note it's 1 sandwich compared to 2 slices of bread. Therefore, 12 compared to 24 slices of bread. 24 is twice as big as 12. In a similar way, 4 slices of ham, 4 times bigger than 1, so 4 times bigger than 12, that'll be 48 slices of ham. And as you might imagine, 36 slices of cheese. So the proportion in the balanced equation has to match the proportion in the change level. And we can subtract all of those numbers, minus 24, minus 48, minus 36, and therefore we know how much of each of these reagents that are in excess, how much of them are remaining. So one of the nice things about this non-equilibrium ice table is you have all of this information in front of you. Here's another example of using a non-equilibrium ice table. And I'd like you to start to get used to thinking about these reactions at the symbolic and molecular level. So this is a reaction of X with 2Y forming XY2. So you can see the balanced equation tells us it's twice as much of Y compared to X. Now we want to think about what would be the limiting reagent. And if you look carefully, I think you can see that all of the Y actually gets consumed because there's no Y remaining at the end of the reaction. So that'll be helpful. But remember, at the initial level, you're just listing everything that's present. So we've got 4 X's and we've got 4 Y's. So that has nothing to do with the balanced equation. And then, of course, no product yet. Now, I just said that all of the Y got consumed. So minus 4Y, 0 remaining. And remember, at the level of change, it has to match the balanced equation. So if it's minus 4Y, well, then how much product will form? Well, it'll be half that amount. And sure enough, that's what we see here. We've got 2 molecules of XY2. So that'll be plus 2 on this side. And then in terms of, well, how much X got consumed? Again, it has to match the ratios in the balanced equation. And therefore, it's going to be minus 2 here. And indeed, we have 2 left over. And of course, that's what we see right here. We've got 2 of these X's left over. And of course, we got plus 2 in terms of the product. So this ice table reflects what happens in the actual reaction. If we didn't see the diagram initially, we could have predicted which reagent would be limiting. So for instance, if you think about our Y and you ask yourself, well, I've got 4Y, how much product could I form? Well, given that the ratio is 2Y for every 1 XY2, well, then you'd say, well, I start with 4, I can only form 2. Whereas if we'd started with the X, so I've got 4 X's, how much product could I make? Well, I would have predicted if all of X got consumed, I would have made 4 XY2. Well, clearly, we didn't make 4 XY2 because we didn't have enough of Y. So Y was the limiting reagent here.